Hey everyone, we are here to start chapter 6, and I'm going to tell you straight up front, chapter 6 is a pretty short chapter, and chapter 6 is kind of unique in that it's not really a chapter full of a bunch of new information, not a lot of new content really. This is more or less a preparatory chapter. The concepts we learn in this will be, more specifically applied in chapters 7 and 8. As a result, this is pretty short, and also I'm not going to assign any homework for this one. A lot of it is review stuff we've done before, and some of the other stuff is more just kind of like learning certain notations or bookkeeping techniques. All right, and it's going to be divided into two primary sections. One of them's dealing with reactions and reaction equations, and another one is a very quick review of some of the stuff that you learned in Gen Chem regarding thermodynamics and kinetics. All right, so let's start off. We're going to talk about reactions here. All right, so the first thing we need to talk about is how do you write organic reactions in organic chemistry? You guys are used to a certain way of doing it in Gen Chem, right? If you have a reaction between A and B, you write A plus B yields C. You go through, you balance the equation, and you be sure to make note of any other things like heat that's given off or taken up, catalysts that are used, that type of thing. Okay? Well, we basically do the same things in organic chemistry, but the way we do it is a little bit different sometimes. We employ a lot of shortcuts, a lot of sort of abbreviated versions of these that can be a little confusing to people coming out of Gen Chem sometimes, but you'll catch on pretty quickly how we do it. For one thing, whenever we write this, a lot of times what we'll do, instead of writing A plus B arrow yields C, we'll kind of just streamline this a little bit. We'll just write A and then a reaction arrow, and you write B on top of it. And then that yields C. I know it doesn't seem like it saves much here, right? It just saved a plus sign, but this is the common way of doing it in OChem. Basically, when you write something on top of a reaction arrow, such as this one, it implies that that is a chemical reactant, and you're reacting it with whatever else is on the left side of the arrow. So this says, literally, A plus B yields C. Okay? So for example, if we wanted to see this in a real life reaction, let's say we had, something like this, right? We're going to react it with OH minus to give you this plus this. Okay? That's how you would write it sort of Gen Chem style. But, one way we could write this OChem style would just be to say, this. And it may not seem that efficient right now, but we're going to introduce a couple of other little things that we can use to shave some stuff out, and it sort of accumulates together to create a little bit more of an efficient system. All right? Okay, so these two equations mean exactly the same thing. All right. Now, another thing that you'll oftentimes see is that in organic chemistry, we are very focused on synthesizing a particular product. All right, and that is our focus. We're interested in what type of product we're going to make and how that stoichiometrically relates to the reactants. One thing a lot of times we're not necessarily concerned about is byproducts, waste products, stuff we don't care about, right? So in this case, if you look at Br minus, that's a waste product. That's just a byproduct. If we're trying to get that molecule, and that product is called, that is ethanol, by the way. If we're trying to make ethanol, we're not really focused on the waste products. So a lot of times what you'll see is that we will, when we write equations, we will omit byproducts. And this is not a hard and fast rule, and this can be a little bit aggravating if you just want, black or white and don't want little shades of gray. But a lot of times you will see the byproducts omitted. It's just kind of something you have to get used to, right? So another way of writing this would be just to omit that altogether and write this. And that can be a little aggravating because, hey, wait a minute, aren't we supposed to balance equations and all that? Balancing equations really is done more by looking to see how many moles of reactive groups from one reactant react with reactive groups of another one. And that's something you kind of pick up a feel for along the way, right? I'm not necessarily expecting you to be able to draw this right now, but we'll learn more about that in chapters 7 and 8. Right, so just because you don't see, it looks like something may be missing here, that's because we've omitted the byproduct. All right? Okay. All right. Now, excuse me. Now, what we just did was what we call a one-step reaction. We just did a singular reaction, took two reactants, converted it into a product. Sometimes, a lot of times, you're going to see as we go through, as we're trying to synthesize something, it takes us more than one step to get there. For example, let's say we had this sequence. Let's say we were starting off with bromoethane. And, whoops, excuse me. Let me write this in organic form, what we care, the way we do it. All right, so let's say we're reacting this with OH minus to give us this product. Okay? But we didn't want to stop there. Then we wanted to use this product and react it with this. I haven't told you, it just occurred to me, I haven't told you about the bottom of the arrow. I'm going to share that with you in just a minute. All right, but let's go ahead and finish this out. This gives you isopropyl alcohol as the product. So basically what we did here was we went on a two-step journey here to convert bromoethane into isopropyl alcohol. All right? And you could summarize the writing, the chemistry that took place in this form. However, organic chemists like to be a little bit more efficient with it. So what you could do is you can take one of your reactants, like this, draw the arrow, all right, and what you do is you make a numbered list of steps. So number 1, the first thing we did was we added OH minus. The second thing we did was we added H2O in the presence of sulfuric acid. And the end result was isopropyl alcohol. Okay? This that I'm putting in the rectangle means the exact same thing as this. It's just a little bit more of a compact way of writing it. And, there's really no limit to the number of steps. We're going to see some of the syntheses, there'll be 3, 4, 5, 6, 10 steps. They can get pretty complex. You can write an unlimited number of steps here. And that can definitely save you a little bit of room, make it a little bit more efficient to note down. Okay? Now, I mentioned the bottom of the arrow. Just like we said, the top of the arrow is reserved for reactants. The bottom of the arrow is reserved for basically anything that's not a reactant. So, other stuff. If you're looking for a really technical term here, other stuff is on the bottom. All right, so this can include several different things. It can include any solvents, specific solvents that you have to use that don't actually react chemically. Catalysts, heat, special types of light like UV light, electricity, flame, etc., etc. There's lots of different things. So anything that's basically not a reactant is put on the bottom. Right? By putting it on the bottom, it tells the viewer that, hey, this isn't going to chemically react or form bonds or anything like that, but it's necessary to get the process to go. Right? So for example, let's say we were trying to convert propane into this guy, which is 2-bromopropane. We need a couple of things. We need a chemical reagent as the source of Br. That's the Br2. But we also need an energy source, a very specific energy source in the form of heat. And heat is commonly represented by a delta sign, uppercase delta sign. That's the triangle. All right? Something like this. This is benzene, and we mentioned aromatic compounds in IR when we looked at IR spectroscopy. We learned that we can put stuff on benzene rings, such as a Cl, right? Well, we need a source of the Cl as a reactant, that's Cl2. We also happen to need a catalyst for this one. Will not work without a catalyst, and that is FeCl3. And if you guys remember from previous classes, a catalyst is something that speeds up the reaction. But it's not chemically consumed, so it doesn't count as a reactant, right? So we put it on the bottom. And yeah, just like you can have several reactants, you can have several other things besides just one catalyst or solvent or whatever. You might have several other things besides reactants. They can all go on the bottom of the arrow. Okay? All right? Very, very good. All right, so let's shift gears a little bit and let's talk about the types of reactions that we're going to see in organic chemistry. And it's kind of funny. You're going to see tons of different reactions. And they're going to be classified largely by functional groups. You'll see, reactions of alcohols, right? Reactions of alkyl halides, reactions of alkenes, etc. And you'll see many, many different individual type reactions. However, all of these reactions can be broadly placed into basically three categories. For right now, we'll see some other broader categories a little bit later, but mostly three categories. All right? And they're pretty simply defined. First one is substitution. All right? Substitution, well, what do you think when you hear the word substitution? You think that one thing replaces another. And that's exactly what happens here, right? So let's say we had this. And let's see, I'll just put in, and I'll write this the Gen Chem way so you can see it a little bit more clearly. Let's say we put in Cn minus. In this case, literally what happens is that the Cn minus swoops in and takes the place of the Br, and then the Br has left, taking this pair of electrons with it. So the Cn minus has substituted for the Br minus. Okay? Whenever you have a substitution reaction, you end up breaking one sigma bond, and that's going to be the Br to carbon sigma bond that we broke, and you're going to form one new sigma bond. So trade for trade, all right? And in this case, the new sigma bond that we form is this carbon-carbon sigma bond. All right? So that is a substitution, and substitutions are actually the focus in Chapter 7, just to give you a heads up. We'll learn a lot more in depth about how we can get substitutions in alkyl halides. All right, the second one that we're going to see, it's going to be eliminations. All right, so let's say we had this. All right, so this is isopropyl alcohol. And just this time, I'm going to draw in one of those understood skeletal structure H's. They're just for illustrative purposes. All right, you can add some sulfuric acid to this. And basically, elimination, well, it makes you, when you hear elimination, it makes you think you're getting rid of something, right? And that's what you do. All right, you end up making this. You end up making an alkene. You see, you have eliminated this OH, and you've eliminated this H, right? If you count the H's on the last carbon, You'll see that we originally had 3, and now we lost 1, right? You also form H2O, water, as a byproduct of this reaction, all right? So we've eliminated water from this molecule. Whenever you do an elimination, you break 2 sigma bonds and form 1 pi. Okay? All right, and then the last type is addition. And again, the name is pretty descriptive here. You think addition? Well, you're adding something to something else, right? You're putting something else where it wasn't before. And that's what we have. And in fact, addition is basically the opposite of elimination. And then in fact, I can show you. If we took that alkene, that same one that we just made, and we added water in the presence of sulfuric acid, which is a catalyst in this case, you create isopropyl alcohol. And I'll draw in that H. Right? So this is literally the opposite of the reaction we just put up. Right? And you see in this case we actually break 1 pi bond and you form 2 sigmas. Now, don't get lulled into a false sense of security here. You say, oh, well, there's only 3 different types. You're going to find out there's a whole lot of ways we can make these additions, substitutions, and eliminations happen. But this sort of gives you a good framework for what to expect in upcoming reactions. All right. So let's talk about, in these reactions, how do we move stuff around? How do we, get bonds to form? How do we get bonds to break? All right? And we've already gone over this a little bit along the way, but I'm going to sort of show you in an applied sort of a concentrated context here. All right? We have done already some examples of reaction mechanisms. All right? You're going to be doing a whole lot more of them, and they're going to get more complex. Basically, what you do in reaction mechanisms is you show the movement. That's sloppy, but it's movement of electrons and atoms as they kind of shift around whenever you break bonds and form new bonds. Okay, and there's a couple of ways that we can go about this. All right, so if we're talking about breaking bonds, let's say we had molecule AB, all right, and we're going to break that AB bond. All right, there's a couple of different ways to do it. Number one, we could break it right down the middle, where each one of these guys gets 1 electron. So you'd form this. That little dot represents an unpaired electron. And we have a and a B, each with an unpaired electron. All right. So what happens is we can draw electron movement, as you've noted. I think I've shown you this in class, with these little fishhook arrows, and you guys have done it on sapling as well. Right, these little curved arrows. Okay. Now, if you only have one, what we call a one-headed arrow, right, just one little line coming off of the arrowhead, that shows movement of 1 electron. So in this case, this bond breaks. 1 electron goes to B, 1 goes to A. And you form this. A with an unpaired electron and B with an unpaired electron. These are referred to as radicals. You may have heard the term radicals or free radicals before. This is what that's referring to, right? Something that has an unpaired electron. And overall, this process is called homolysis. Splitting of an electron pair evenly between atoms. All right, one thing you might notice is that this process does not produce ions. It does not produce charged species. It just produces radicals, which are defined as being neutral. Now, there's another process, another way that we can break these bonds, where we do produce ions. All right, so let's draw this again. Okay, so again, we're going to break this AB bond, but this time, we're not going to split it right down the middle. What we can also see is that this whole electron pair might end up going to one of the atoms involved. All right? In this case, we draw a double-headed arrow. That means you're moving 2 electrons, right? 2 electrons or 1 electron pair. So that means the B gets both the electrons. So it's got an extra unshared pair. And since it was neutral before here, we can see now, since it's gaining a pair of electrons, it's going to go negative. Whereas the A, it was neutral. Now it's losing a whole electron pair. It's going to go positive. Okay? This process is called heterolysis. And heterolysis produces ions, right? Positive ion, it's called a cation. Negative ion is called an anion. You know how you can not get them mixed up? If you're a cat lover, you regard cats as being positive. That makes it easy. If you're not a cat lover, well, sucks for you. That makes it harder. But either way, it's not too hard to remember. All right. One thing that's important to note is that since we're, in organic chemistry is about carbon-containing species, right? So, a lot of times we're going to see charged carbon species. For example, let's say we had this guy. All right? In this case, it's very possible for this Br minus to detach itself from that carbon. So it gives you a Br minus. All right, and it also leaves this carbon right here positively charged. A positively charged carbon is not just a cation, but it is a carbocation. And we will be talking about carbocations much more than you even would ever want to know starting next chapter. So good time to go ahead and get that terminology into your brain. All right. It is also possible. They don't occur as commonly, but they do occur, certainly sometimes. You can also have negatively charged carbons, right? So something like this, right, where this middle carbon has an extra unshared pair of electrons. That is called a, I want to erase some of this stuff so you don't get confused. This is called a carbanion. Not a carboanion, carbanion. All right. Okay. So be sure to review some of this. One thing of note here is that, we mentioned these different types of arrows. If you need a little bit of review and just need to keep these reaction arrows straight, there's a nice table in Chapter 6. I think it's Table 6.1, but it might be different in your edition. That has sort of a summary of the different arrows that are used. So use that. Feel free to use that as a reference to kind of help you remember which one to use at the appropriate time. All right, and that sort of wraps up this part of the chapter. There is a portion of the chapter here that's called bond dissociation energy. We are going to skip that one altogether. We're not worried about bond dissociation energy. The next part is going to involve thermodynamics and kinetics, and that will be the subject of the next video. All right, until then, I will see you later. Bye-bye.